All right, so been a while. We last were talking about math, I think, but no guarantee as to if that's actually true or not. um, we're gonna continue on, but I don't know. I'll talk kind of at the end of the class about more details about what school's gonna look like in general, and you know, PFAs or homework or stuff like that. But for right now, let's just go into it, do some stuff. If you have a question, then I know it's kind of hard. One, because the actual stream broadcast, about anywhere between 3 to 8 seconds behind whenever I actually record it. So chat's always a couple seconds behind me. And also I know it can kind of take some time to type out a question depending on what the question is. So if you have a question during the course of a class, then if you have a question throughout the course of the class, then just type something in the chat like question or wait or hold on or stop or something like that. Then I'll know to pause, and then that can give you time to type out whatever you have to say. So just I try to keep my eye on the chat. Just some sort of alert to me that I need to chill out for a second while you take some time to type. Okay. But yeah, so we're all living in the age of RJ right now, right? It's a tough world. We need to empathize with him and understand that this is a real serious issue that people deal with. Okay. All right. So let's go ahead and start off. We left off talking about polar stuff. I don't know how well the polar stuff went whenever I was gone. Maybe maybe good, maybe bad. I don't know. What do you guys think? Whole class is here. We got a good amount of people here. Okay, so it went so well that you were crying tears of joy. All right. Okay, that's about what I was expecting. So we're good. Great. Let's start off then just with this example of one of the days that we missed. Okay. Talking about area shared between two polar curves. All right. So if we remember from doing area underneath a curve, it's more like underneath the curve, between the curve and the origin almost. That our general formula is 1/2 the integral of the radius squared d theta. Right. Now, it's a little bit different then when we talk about what is the actual area, for example, shared by the two polar curves. So area between, or the area that's inside both of them. So we can kind of see, in general, it's not crazy hard to pick out that this highlighted region is the area that is inside both of them. It is the common area. It's the intersection. I don't know if you want to think about it like that. But here we go. Now, one of the biggest parts of finding these areas is that we are typically going to want to kind of split up pieces, right? Because, for example, this piece right here, this area is only, I can determine that only being determined by that red curve. Okay, so I can make an integral that says, okay, well, just find the area specifically from here to here, right? Or if I want to think about these two individual pieces, or I can think about that whole as across as one piece as a whole, depending on how I want to do it. And then I have this secondary piece, which I'm outlining in this blue line, which is just this semicircle that's determined by the blue circle. Right? So I'm basically wanting to take three smaller pieces of areas and add them all together to say what is the first final area, or first final area. What is the final total area? That's the word, I think. We can do this in a couple ways. First thing, though, is I want to make sure, some of these are easy to see, but I want to make sure I know where are these intersecting so that I have a good idea of where is it that I should be integrating from? What are my bounds? Okay, so to do that, we'll first just take our two equations and set them equal to each other. So 4 equals 4 minus 4 sine theta. Subtract 4 from both sides, divide by -4. So I get 0 equals sine of theta. Yep, chat's blowing up right now because everybody knows the unit circle so well. So we know that sine of theta is equal to 0 whenever theta is either 0, pi, or 2 pi, 3 pi, 4 pi, 5 pi, 7 pi, etc. on into infinity. But so I know these points of intersection are happening first if our theta is 0, and then second as my theta is pi. Okay, and we can see that works well as we go around the circle. So just first as my angle 0, great, I get that point exactly. Pi over 2 would give me back in the origin, and then as I go to pi, that's that second intersection point. So it's something that we can sort of visualize sometimes, but sometimes can be deceptive. So we do want to go ahead and actually do this solving portion so that we know for sure where the intersection points are, because depending on how weird the equation is, sometimes it might not just be as easy as being able to look at the function and say, oh, they're right here. Okay. Okay. So first thing I'm going to do is I'm going to find the area of one of these sections that looks like this, right? So for example, maybe this first area here. Okay. We can do this just the normal way of finding the full area, or we can do this by symmetry, because I see that these two pieces are exactly the same, okay, just on either side of that y-axis. So we can find an area that goes from 0 to pi, or I can find an area that's 0 to pi over 2 and just multiply that area by 2 since there's two pieces. Doesn't matter which way you do it. I'm going to go ahead and do it by symmetry. Right, so my first area, so the formula I know, 1/2 the integral 0 to pi over 2, because that's right from 0 to pi over 2, so that'll give me that first highlighted area that I want. R squared, so this is bound by the red curve, which is this one. So 4 minus 4 sine of theta squared d theta. So that would give me the area for one of those pieces. But like we said, we have two of them. So actually, whatever that area is, I want to double it. I want to multiply it by 2. Okay, so I'll do that. Now that works out nicely that I have 2 times 1/2, so this will just end up canceling. So it's just whatever this integral is. And then So that's the area just for those two top pieces, those kind of humps. Right? And now for the area of that semicircle, well, it's not crazy hard to find the area of a semicircle, but let's just practice doing the integral way and using symmetry as well. So again, I can do this. I could either say, all right, let's just integrate from, well, here, let me set up my integral first. So 1/2. I'll write it over here so that I can add it. Because I'm trying to find a total area, so I'm adding things. So 1/2 the integral of r squared. So that's this part now that I'm looking at, this bottom half of the circle is bounded by r equals 4. So r is just 4. So 4 squared d theta. And so now I can choose my bounds and choose whether or not I'm going to use symmetry. Okay, so one option is I can just go from pi to 2 pi, because that would get me here, over here at pi, and then all the way around to 2 pi, right back at the beginning. Right, I could do that, or I could say, actually, just go from pi to 3 pi over 2, so that would give me this portion right here. But then I know the other side of that axis is the same, so using symmetry, I say, okay, well, whatever that area is, just double it. Right. Just kind of trade-offs. Now, what's nice is that's cancels again, so 2 times 1/2, well, it's just 1. So I've gotten rid of needing to worry about the coefficient part of it. It makes my bound a little bit, tiny bit messier, that now my upper bound is 3 pi over 2 instead of just 2 pi. But whatever. I don't know if you guys particularly like doing the symmetry way or just doing the normal way. I don't know. Feel free to comment. In the meantime, I'm just going to clean this up a little bit. d theta. Okay. Once we get to here, we just need to calculate it one way or another. So we can use, you can use your nice graphing calculator if you so choose, if you really love that. You can use Desmos. You can use, Symbolab. I don't know. Either way, since you guys are going to be at home a lot for the next decade, one thing you could do, so I'll show you how to do this on Desmos, if you don't already know. Okay, for Desmos, you're totally able to do lots of calculations and integrations as well. So for example, if I want an integral on Desmos, if you just type in int, it will create an integral right there for you. So that's nice. So 0 to pi. So if I actually just type in pi, it'll make pi for me. Divided, so I'll just hit /2. I'll put my 4 minus 4 sine Same thing for theta, just type theta, it will make it. And then d theta. So there's that first expression. It just automatically calculates it. It's about 5.699. Okay, but that's not the full thing I want. So I'm going to go ahead and actually add my other integral too. So I'll just type int pi for my lower bounds, 3 pi over 2 for my upper bounds, 4 squared, you know, is 16, but whatever. D theta. Okay, so there's my actual full expression. That it equals about 30.832. Okay, so I don't know. I don't have a graphing calculator on hand that I can actually use in my hands. I can use it on my laptop. I can use it on my computer here, but then it's slow because I have to actually do the mouse clicks to do everything. So this is faster for me. I'll typically do that. I don't know if it's faster depending on if you actually had a graphing calculator in your hand or not. Maybe. But it is nice, and it will just immediately calculate it. So pretty cool. So let's go back. And again, on Desmos, just whatever if you want some sort of symbol, usually if you just type it. So for example, int makes the integral, pi makes the pi symbol, literally typing theta, theta makes the theta symbol. You can do whatever you want. Yeah, let's come back to Smart Notebook. It's 22 people on the stream. Is there? We're blowing up. 22,000, that is. Sorry, not just 22, but yeah, a good, not bad. I was hoping for 25,000, but it's not bad as well. You know, you do what you can. First day, first stream, so makes sense. It's a little low. So our final answer is that equals, I already forgot what I said, 30.832. I mean, in these trying times, maybe there's truly nothing better to do than watch my calculus stream. It's come to this. This is what entertainment is now in 2020 Anno Domini. Questions about this warm-up? It's basically just adding up all the little pieces, right? However many areas you need. In this case, there was 3 pieces or 4 pieces, depending on how you think about it. But we can use symmetry to just eliminate it down into 2 integrals. 1 integral for the top symmetry part, 1 integral for the bottom part that also had symmetry, so it helped a lot. Oh, goodness. Emily got her coffee. She's sad that she wasn't allowed to pay $7 for a Starbucks drink, but you know, got to do what you can. All right. So today we're going to talk about polar arc length and surface area of revolution. So 2 things that we've done before, We've done arc length for normal equations. We've done normal for rectangular equations, just y and x. We've done arc length for parametric equations. Same thing for surface area of revolution. So if I take some curve, spin it around an axis, it creates a 3D shape, and I want to know the surface area of it. So now we're just going to do that with polar coordinates now. We're not going to do this a ton. It's something that I don't know. It is a bit difficult, but we're not going to spend a ton of time on it. I think there's bigger fish to fry, especially given the current circumstances. Remind me at the end also when I'm kind of talking details about school to talk about the AP test, because I have a few bits of information about that if you haven't seen things already. Reminder for arc length for parametric equations, and remember, polar forms, polar equations are just a form of parametric where, parametric, we have an x equation, we have a y equation. So x equals r cosine theta, y equals r sine theta. So it just so happens that we call this specific type of parametric equations polar equations. Man, that is really ugly. It's not my fault. I'm lagging. Just keep that in mind. Where's the prime stuff? Coming soon. As soon as those thousands of viewers pick up. Okay. Arc length of polar curves. So this is tentatively our formula. Not exactly. This is just the parametric formula, right? For arc length, if you might remember that, it was dx dt square root of dx dt squared plus dy dt squared dt from a to b, whatever. That's the same formula that this is showing right now, but instead of writing dx d theta, it writes x prime of theta, same thing. Instead of dy d theta, it's writing y prime of theta, same thing. So I don't know, I was kind of conflicted on how I wanted to present this. If you need to, just remember polar is a type of parametric, and just use the parametric formula. All right, it'll still work. Now, certain things happen though when we do dx dt and dy dt, or dx d theta, dy d theta, because remember, if we're doing x prime of theta, we have to do the chain rule, because this is actually r is some equation that we're given. So it could be like r is 2 plus sine of theta and then times cosine theta. So if I want to take the derivative of that, I need to do the chain rule, or same thing with the y. So it can be kind of ugly. But it turns out if you just do this in general and you do the chain rule and you move some things around and manipulate some stuff, we end up with this formula. All right, whereas it's the square root of r of theta squared. So this is just our original equation. And r prime of theta squared, where r prime is just the derivative of the original equation. Either way is fine. It doesn't really matter. This formula is a bit nicer because you probably won't need to end up doing the chain rule. We only have to do the chain rule with the other one because Can everyone still see and hear me okay? My screen just kind of freaked out for a second. Am I still live? Okay. Back. Cool. Yeah. Sorry. Don't know. So just a lot of PogChamp in the chat. Perfect. That's what you like to see, you know. That's why I worked my whole life, high school, went to college, got my degrees, got my masters, just so that one day I could be quarantined in my house while my students watch me on Twitch putting PogChamps in the chat. That's what more can you ask for? That's what this has all been about. And I'm just so thankful that this day has finally come. But so do it this way. You're going to need to do chain rules for the dx d theta, dy d theta. You do it this way. It's nicer that you don't have to worry about the chain rule, but it is just then another formula to memorize, because I know you guys have 10,000 formulas already that you have to memorize. So I don't know, up to you. So let's just do a quick demonstration of that. Find the arc length of the polar curve from 0 to 2 pi over 3. And my polar curve in this case is 2 minus 2 cosine theta. So actually, before I do my integral, so I know already what r is. So I just need r prime. All right. R prime, derivative of 2 is 0. Derivative of negative 2 cosine theta. That would be positive 2 sine of theta. And now it's just a matter of putting this into my formula. So from 0 to 2 pi over 3. And square root. So r squared plus r prime squared d theta. If you just love the parametric formula so much, right, and you don't want to memorize the polar curve, that's fine, but you're going to have to do the parametric formula. So x equals r times cosine theta. So r in this case, 2 minus 2 cosine theta times cosine theta. And y equals r 2 minus 2 cosine theta times sine of theta. Perfect. All right. And then when you do dx d theta, dy d theta, you're going to have gross chain rule. And so, I don't know. If you really want to do it, it's going to be a heck of an integral that you end up typing in, though. Okay. So this one, though, is not too bad. Okay, pretty nice. So let's do our... Where did my Desmos screen go? Okay. So again, you can do this on your calculator, do it in Desmos. So 0, 2 pi over 3. If you want the square root symbol, type SQRT. Boom. 2 minus 2 cosine theta squared plus 2 sine theta. Where'd it go? Okay. Squared. Okay, if you're a little bit confused, on sometimes if you type in the integral and you're like, well, it's not working, and you get this little, exclamation point, something's going wrong. It's just because you need to still put the d whatever on the end of the integral, so d theta in this case. And we see, oh wow, after all that, it equals a nice, perfect 4, which is pretty incredible, actually. Interesting. Let's see what that graph looks like. We get 4. Yes, you still have to sign out to go to the bathroom. You gotta check the playlist in Summit. There's a sign out sheet, right? And you'll be good to go. It took 25 minutes. Hi, RJ. It's good to see you, buddy. 25 minutes later, the stream starts for RJ. Oh, man. Some things never change. I love it. Damn, probably. I'm always the afterthought. Oh, yeah, Mr. Abundance is here. All right. So there's a quick arc length for polar formula. Right. Square root r squared plus r prime squared d theta. It's from wherever you want. Also a reminder, in parametric, arc length is the distance traveled formula. So just let me write that down here. So this at the bottom, I forgot to delete that. This at the bottom is from a different problem that I originally had here, but I got rid of it, so don't worry about that. Oops. Okay, but remember, in parametric or polar is just a type of parametric. If we want to know distance traveled, it's bugging out. If I want to know distance traveled, what that's asking me for then is arc length. Keep that in mind. We have a separate distance traveled process if we're talking about rectangular coordinates of just x and y. But parametrically, if we want to know distance traveled, we're just using the arc length formula. Or for polar, if we're doing distance travel, it's just the arc length formula. So that's pretty nice. Okay. All right, next up, surface area of revolution. To find the surface area by revolving a polar curve around an axis, we're going to do this parametrically. So remember, surface area of revolution is the product of the circumference and the arc length. So because you perfectly remember surface area of revolution when we did it before, it turns out the formula is just take the arc length formula we already know and then multiply it by whatever the circumference of the object is. So the circumference will change depending on what point, but that's the basis of it. For x-axis, okay, that means another way to say that if we're thinking about polar equations is we're doing it around the polar axis. And if we're revolving around the y-axis, that's another way of saying we're revolving around the line theta equals pi over 2. Right? Because pi over 2 is that upper right angle. So we go straight up and down. So some interesting formulas here. They got a lot going on. Okay. But keep in mind really what these actually are. Okay, remember that in either case, this is just the arc length formula that we had before, right? No change, no difference. Okay. The 2 pi out in front, or actually, right? 2 pi r is circumference, right? That's just, if I'm given a circle, that equation is 2 pi r. Okay, so we have basically exactly what we just said on the last screen. We have the circumference times the arc length. Right? So the only difference now is we have this sine in here and this cosine in here that kind of mix it up a little bit. And the reason if we're talking about revolving around the x-axis, okay, and I want to know what that radius is as I revolve around the x-axis, well, the radius is just whatever. If I want to know how high is that, well, it's just whatever the y value is at this point. Right? What is that y value? Well, if I want a y value, think back to our polar process, our polar substitutions, right, that we have y equals r times sine of theta, which is exactly what that piece is. Or same thing if we're talking about revolving around the y-axis, and I say, hey, what is, since I'm spinning around that way, well, what is that radius? Well, it's just how far is it over from the y-axis. So that radius would be whatever the x value is. Well, from our polar coordinates, we know x is r cosine theta. Right, so that's why it's not just the 2 pi r and the arc length, or not just 2 pi r and arc length. We have to account for, are we talking about the x value or the y value? Because if we need that y value, because we're revolving around the x-axis, then it's not just r, it's r sine. So does the revolving around the polar axis make a big spherish type thing? Up here, for these examples that I drew, yes. Since I just drew them each to be a semicircle. So, well, I mean, because I drew it perfectly to scale and everything too. So assuming this is a perfect semicircle, if you spun it around the x-axis, yeah, it would just make a sphere. And same thing for this one. It's just a semicircle. So if I spin it around that y-axis, yeah, it would make a sphere. Those are just easy cases though, so it's not always that we're just making a sphere. But so depending on what the curve looks like, who knows? But yeah, in these cases, it would make a big spherish type thing, as you put it. So I know these equations look awful, and they are sort of awful, but it is just circumference times arc length. Very smart, very smart. You know, kind of interesting that up here, unlike Intel Unite, when I click save, I don't have to automatically restart everything. It just saves it and nothing breaks. Isn't that crazy? All right, so let's do some examples. Find the surface area generated by revolving r equals 2 cosine of theta around the line theta equals pi over 2. Okay. So I'm thinking about revolving around the line theta equals pi over 2. That is a fun way of saying the y-axis. Now, as we build our integral, so I know that part of the formula is I can just kind of start out with my 2 pi out in front. No big deal. And then r of theta, so whatever my equation for r is, which in this case is two cosine theta. Now I'm revolving around the y-axis. So whatever I want the radius to be is just going to be however far away the x value is. Right? So remember that if we go back to over here, right, revolving around the y-axis, then we're looking at the x value. So I need a cosine here as well. So I already have a cosine from the original equation, but I also need another cosine that's just part of the equation sort of to account for that this is an x value. So this is just r times cosine theta. Right. And then the other thing I need is the arc length. So that accounts for the circumference, but now I need to multiply that by the arc length. So my arc length of r of theta squared, so 2 times cosine theta squared, plus r prime, I'll do it up here, will be negative 2 sine of theta. So negative 2 sine of theta squared. And then pretend I had enough room for my d theta here. Except let's make that not an ugly letter D. It's still a little ugly, whatever. D theta. So now I just have to decide what my bounds of integration are. Okay. So I need to think about is kind of a bit different. I just need to think about what will create this circle. Okay. What angles of theta does it take to actually draw this full circle? So we might, this is a little misleading. Let me pull Desmos. Yes. Okay, let me pull Desmos back up. And let me find it so I can type it. Okay. You can graph on Desmos if you want. Just do R equals, so 2 cosine theta. I'll even make this my nice polar settings. Switch right here. Make it a bit easier to see, maybe. So here's my graph. There's way too many lines. Let me take these off. Just no numbers. Okay. So if the most common thing that people think is goes 0 to 2 pi, like because we think of a circle as 0 to 2 pi, which makes sense. Okay. No problem there. But it actually doesn't take the full 2 pi in order to make this circle. So for example, if I just do 0 to pi, it still has the full circle. Now if I kind of try other things, so 0 to pi over 2, okay, pi over 2 gives me half of the circle, you know, or pi over 3 gives me a portion of the circle, or pi over 5 or whatever. But the point is, all it takes for this circle to get drawn is just from 0 to pi. So for my bounds of integration, I'm just going to use 0 to pi. And so now I'm going to type all of this in. So I had 2 pi from 0 to pi. Two cosine squared theta times square roots two cosine theta squared plus -2 sine theta squared d theta. All right, so that's my full equation. So let me go back so you can see my Desmos or my notebook screen for a second. So let me just clean this up a little bit. So 2 pi 0 to pi 2 cosine times cosine, so that's 2 cosine squared times square root of, you can actually do those squareds inside of the integral if you want to, or you can just, either way. D theta. Doesn't matter. But that's exactly what I typed in to Desmos, which, let me just look back really quick. So it's about 39.478. So it's a little bit of process to set up, but other than that, it's fine. Okay. Grant, why does 0 to pi work and not make half a circle? Good question. So let me pull back up my graph really quick. Okay, so let me get rid of all this crap. 0 to pi works in this case just because of how, since it's based on cosine. So if you kind of think for a second on what happens when I plug in different values of theta here. So like, for example, if I plug in 0, then cosine is 1. So 2 times 1 would be 2. So that would give me this point right here, this very furthest out point. Now, if I go to, let's say, pi over 2, okay, 2 times cosine of pi over 2. So cosine of pi over 2, cosine of pi over 2 is 0. 2 times 0 is 0. So that would give me this other side of the circle. Okay. And then to go back, again, to get back to 2 pi, cosine of 2 pi is 1. 2 times 1 is 2. So I'm right back to where I started. So it's because of cosine, right, just goes through all the values of cosine. It just, the wave, it goes up and down. So it just repeats. So after we get to pi over 2, it already starts repeating, but just going backwards. So 0, my first point starts here at 0, right, or the value of theta 0. And then as we're going, we're plugging in more thetas. We get to pi over 2. So when theta is pi over 2, we hit the origin. And then after we've done that, we've already now gone through every possible value that cosine can be. So now from going pi over 2 back to 2 pi, it's just going to be those same values again. So it's just except, okay, so same values traces out the other half of the circle, right? So we don't need the full 2 pi in order to do that. We just need 0 to pi in this case. And again, if you're ever not sure on like, wait, what theta values actually trace out what on the circle, just on your graphing calculator or on Desmos, just plug some stuff in and see, 3 pi over 4. Oh, okay, so that traces out 3/4 of the circle. Right, so that kind of proves to me that, 3 pi over 4, so 3/4 pi gives me 3/4 of a circle, so that would make sense then that 0 to pi would give me the full circle, right? Or 3 pi over 2, that gives me a full circle because that's bigger than pi, so it just repeats and starts tracing the circle again, so I don't need that. Pi over 2 gives me half the circle, right? So it's just because of cosine and sine. Hopefully that helped. So let's do one more. Find the surface area generated by revolving r equals 4 sine theta around the polar axis. Okay. So now we're talking about the polar axis. That's another fun way of saying that it's the x-axis. So when I start to make this, just remember what we're doing here. We're finding surface area. So I know I'm going to start off with the 2 pi. If trying to find the surface area of a circle, does symmetry work with that too, since half gives you the semicircle? So let me go back. That's a good question. I would think so. Let's test it for sure. Let me go back. So let's change my Desmos bounds. So let's say this integral, instead of pi, is pi over 2. But then we would need to multiply by 2 in front since we're doing double that surface area. So yeah, that works. That's great. That's awesome. Good stuff, Reese. So yeah, it works nicely. Now again, you have to be careful because circles have perfect symmetry. So that works well with them. So certain other cases, if it's not, you have to be careful about will the symmetry work. But otherwise, yeah, in this case, we can see that it definitely does. So that's awesome. Good observation. All right, so back to this one. Surface area, 2 pi. Integral r 4 sine of theta. Now, in this case, since we're revolving around the x-axis, so my radius will be whatever the height is of the circle at any given particular spot. Okay. So if I want to know what a height is, well, I'm thinking about a y value. So we need this sine of theta. I don't know why I'm writing so diagonally. We need this sine of theta in order to account for that we're doing a y value. So this is okay. This is a y value. It's the radius, the equation for radius times sine of theta. Right? It's the y value. It's the height. So we know that radius. And then times square root of for sine theta squared, okay, plus the derivative of r. So for cosine theta squared. Hopefully that all fits on the screen. I think you guys can just see that barely. And I always leave off the d theta because I never have space for it. Cool. All right. So that blue part is just the arc length formula from before. Right? The blue part is the arc length formula. And then the rest of it is just circumference, 2 pi r. Right? The problem is we have to make that whole y value because we're talking about polar coordinates. So the whole y value is r, the radius, times sine of theta. All right, so it makes it a lot messier. But at the core concept, it's not an insane formula, but it looks really nasty once you end up having to write out all the garbage. So same thing really quick. I need to decide what my bounds are. So I would intuitively, I first think of like, oh, circles, 0 to 2 pi. But we can see again here, it's actually not quite the case. So r equals, let's see, 4 sine of theta oops. Okay, so I see again, I have pi over 2 gives me half a circle. My initial thought of, oh, 2 pi, well, it does give me a full circle, but let me double check that I'm not being tricked here. 0 to pi actually just works as well. So we don't need the full 2 pi, and we don't want the full 2 pi because if we start tracing over it, then it'll trace out more of that volume as well. Or surface area, sorry, not volume. Okay, so just do some testing on your calculator. As long as you're in polar mode, then whenever you click window, you should be able to choose what you want your theta minimum to be and your theta maximum. So you can, go 0 to pi, 0 to 2 pi, pi over 2, whatever. Okay. So for my integral, so again, like before, let me just clean this up a little bit and give myself some more space so I'm not writing on the edge of the screen and diagonally like an idiot. So I'll actually go ahead, since there's that 4 inside the integral, I can move it out as a coefficient. So 8 pi, the integral of 0 to pi, sine times sine, sine squared, and then, I don't know, if you want to write it out, you can. If you want to just write things in the parentheses with the squares on them, you can, up to you. I'll go ahead and square it. (16 sine squared theta) plus 16 cosine squared theta. Since this is our last problem, I'm actually going to clean this up a little more. So just for the case of we're AP testing and this is a problem maybe where we don't have calculator, or maybe it's a multiple choice where sometimes they'll just say which of these represents the surface area, and it'll give you choices that are just like a bunch of different integrals, so you have to pick the right setup. But maybe you don't see any of this here. So one thing that I'm going to notice is that I can factor out 16. From each of those, which is pretty nice, because now I'm seeing in the parentheses here, okay, everybody perfectly knows all their Pythagorean identities, all their trigonometric identities, all their unit circle stuff. But sine squared plus cosine squared, I really hope we all at least remember, is 1. So Can you enter in your answer as a decimal, please, RJ? Because I'm not quite sure what this number just means by itself. So this is really just square root of 16. So square root of 16 is 4. So I can pull out the 4 as well. So 8 times 4, so that'd be 32. So 32 pi So again, not uncommon that you will see questions like on AP that are which of these integrals represents the surface area of, or which of these represents the arc length of. And so even though it's not the exact formula, just how you immediately enter it, maybe if you simplify some stuff, then the answer, you can see what it is. All right? And this is just easier to type in. All right? And you could pretty, depending on your recognition of factoring and knowing trig identities, you could go right from here to here without needing that middle step. Okay. So it can become a quicker process. It's not like it takes lines and lines and lines of work. But I'll go ahead and type in this integral. So 32 pi, the integral 0 to pi, sine squared theta d theta. 157.914. And also, like Reese had mentioned before, if we wanted to use symmetry with this instead, we could also do that. Instead of going 0 to pi, we could go, well, I think we go 0 to pi over 2 and do it as well. Okay, but again, just be careful. Make sure that that's actually giving you half, and you can use symmetry depending on what you're rotating around. Any questions? Wonderful sports knowledge, Grant. Yes. Okay. So, well, okay. So first, school-wise, we're going to be here at least a month online. I know nothing, and I'm not important in terms of making any decisions in our school or the city or anything. But I would not be surprised if we didn't end up going back the year as well. Now, who knows? That's a long ways away, so a lot can change even week by week. But it wouldn't shock me if we were out just for the rest of it. In terms of what school looks like for like PFAs, performance tasks, things like that for math, I don't have a definitive answer for you yet. We have a virtual staff meeting this afternoon, and so hopefully we get a lot more information and details so that I can then relay that information to you. I imagine we're just going to have to be approving PFAs for you while you're at home. I don't know what that'll look like. Maybe there'll be like a specific PFA window, like every day, like between these 2 hours a day, you can take PFAs, and teachers will try to, monitor on dyno or whatever best we can. I don't know. We'll see. But I know that from what I've understood from communication so far, PFAs are still a thing that still are going to need to get done in some capacity. I just don't know what specifics that'll look like. Homework wise, I'll still give you stuff to do. Things like that. But I'll probably be what I will be doing for us for sure is, since I won't be like sending out homework that you're not going to return it to me, and I'm not going to ask you guys to all send me screenshots of your homework or stuff like that. I will be assigning stuff more through like the AP website. Things that I will still put in as like checkpoints. So like we did earlier in the year, we've done like multiple choice questions that like assignments that we can do. So I'll be doing that. That will, have a checkpoint in Summit every week or two, something like that. That's my thought right now. Performance tasks, I have no idea what they'll be like. So we'll see what they say. And as for AP testing, so did you guys get like an email from AP or anything like that? No. Okay. That's fine. I think they're still working out specifics. We got some initial communication from the AP College Board, saying that the AP tests are still going to go ahead, at least as of now. And it's going to be a modified format that they're going to be the talk was like that it'll be like a at-home exam that will be mostly all FRQ based. So all free response question that will be like 45 minutes long. That was the initial communication that went out, and I would have to go back and read more specifically, but I think that's sort of the plan. Again, I have no idea what the actual logistics of that look like. I don't know. I guess maybe they send you something or send you a link that's like only open for this certain 45-minute testing window or something, and it's all FRQ. So I don't know what that'll mean. I don't know if that they want you to like take pictures and upload it of your work, or or how many questions it'll be. I don't know. So it'll just depend. That's as far as that's the information I know or have right now. I'm not sure. I don't know. Any questions for me in general specifically about like school or AP? Again, I don't have a ton of detailed information, but I can tell you what I know. How will ACT work? As far as ACT goes for us, like how we were going to have the ACT at lead, it's just not happening. It's canceled. And now I don't know if they're operating under the assumption that maybe we'll go back and like on the 24th or whatever, if there's ACTs then. I don't know if that's the plan. I don't know what ACT in general is doing. Like if all testing has just been delayed or canceled or postponed or whatever. I don't know. That's a really good question. But I know as far as lead goes, we can't administer ACT at home or anything like that. Good question. Yeah, good job, Forrester. Thank you. Okay. As far as class, again, I don't know what a lot of stuff's going to look like, but I know that I'll at least be here at this time still doing notes and stuff. I can say that as much. And we'll go from there and see what happens or what works. So do we only have assignments every other day for classes that aren't calc? I don't know. I don't know what other teachers are doing. I think a lot of teachers are doing stuff through Schoology. So make sure you are logging into Schoology every day. They want you to do that. That'll be a big thing. Log in, check stuff, but I really don't know what other teachers are doing. I just know that I'm here streaming, trying to get to 100,000 views as quick as possible. Yeah, Schoology I think has been pretty buggy for some people, but then not for others at all. I don't know. That's why I didn't want to use Schoology, because I know that Schoology is kind of weird sometimes. So that's why I'm on here doing stuff and then putting stuff on YouTube. If it's down for you, I don't know. Maybe just if you're super diligent and great student, then I guess you'd be emailing the teachers directly to ask them and saying, hey, I can't log on to Schoology. Is this? No problem. Hope it goes well. Please just make sure, like, during the actual class and stuff, please keep things calm. All right. There was a moment there and a couple moments towards the middle where we were losing it in the chat a little bit. So please don't make it that I have to like just disable the chat altogether, because then that ruins the whole point. The whole point of doing this on Twitch is that I can engage with you guys if you do have questions and stuff like that. So please don't. I mean, I know there's already people or whatever, but please don't be just trying to get people in here who don't need to be in here, because it ruins it. So, I mean, if I have to at some point, I'll just disable the chat and do this live and talk to myself, but I don't want to do that because that's not the point. School canceled. School is postponed. In-class school is postponed until April 24th, but we are still hosting online and in online activities or classes or material or whatever. I don't know. Check Schoology if you can. But again, if you missed the stream, go to my YouTube channel. I'll upload stuff. I have a break in between now and my next block, so I'll usually try to upload in between this spot so that it's good to go by the afternoon. But if not, then I'll upload it later in the afternoon, this video, so you can see it there. Or if you want to go back and watch again or pause things, like I said, whatever. Okay, so just to be clear, that's a huge joke. National Guard's not doing anything to us. Okay, any other final questions regarding math, this class, or AP? Okay. All right, guys. Well, it's been real. I will see you guys tomorrow, same time. good luck. If you have any other questions, otherwise, email me. Also, I have office hours at 1:45 to 2:30. So just let me know. See you guys. Have a good day. Good luck with your online stuff, and good luck with Schoology. Emily, put the coffee down. Okay, you don't need it. It's fine. All right.